Hi, everyone. So we have 5.1 today, area and distances. Last class, we talked about how uh, we have antiderivatives, which undo a derivative. Well, now we're going to learn that an integral can also find areas and distances, meaning like areas under a curve. So we're just elaborating on why we care about integrals. Here we go. 5.1, area and distances. In this section, we discover that trying to find the area under the curve or distances traveled by a car, we end up with the same special type of limit. Why would a biologist be interested in calculating an area? A botanist might want to know the area of a leaf and compare it with the leaf's area at other stages of its development. An ecologist might want to know the area of a lake and compare it with the area in previous years. An oncologist might want to know the area of a tumor and compare it with the areas at prior times to see how quickly it's growing. But there are also indirect ways in which areas are of interest. We will see at the end of this section, for example, that the area beneath part of the pathogenesis curve of a measles infections represents the amount of infection needed to develop symptoms of the disease. But we begin by attempting to solve the area problem. So find the area of the region S that lies under the curve f of x from A to B. So here's S for area. This is the curve we're referring to. So this is F. We start at A, we end at B. However, it isn't easy to find the area of the region with curved sides. We all have an intuitive idea of what the area of a region is, but part of the area problem is to make this intuitive idea precise by giving an exact definition of area. So we'll get further and further into that, mainly when we hit 5.2. So for now, we're still kind of just going to slowly get there. Recall that in defining a tangent line, we first approximated the slope of the tangent line by slopes of secant lines, and then we took the limit of these approximations. So right here, if y'all remember, that's when we did the limit definition, right? Taking the limit of the difference quotient is what we did. So we're going to do a similar, not exact, but a similar thing here. We pursue a similar idea for areas. We first approximate the region S by rectangles, and then we take the limit of the areas of these rectangles as we increase the number of rectangles. So basically what we're going to do is make this one big rectangle, or maybe multiple small rectangles. And as you can imagine, the smaller amount of rectangles that we have, ideally all of the same width, right? The more precise the area will be. Sometimes we might have an underestimate, okay? And other times we might have an overestimate. It just depends. Okay, so over here, we used what we call right-hand limits. These are right hand. And here we have left hand limits. Because you take where you end on the function and you go to the left hand of the rectangle and you go over. Left hand of the rectangle and you go over. These are right hands because you go to the right hand portion of the rectangle and you go over. The right hand portion of the rectangle and you go over. So basically we're going to just add up a whole bunch of rectangles. That is the idea between 5.1, just adding rectangles at the heart of it. So example, using rectangles to estimate the area under y equaling x squared. Sorry, let me zoom this in a little bit. There we go. Just from 0 to 1. Okay, so we are just going to have one big rectangle. So 0 to 1, this is just the right side of the parabola. This is the point 1, comma 1, 1, 1, here's 0. So what we're asked, if I just do a right-handed limit, well, the area of this rectangle, remember area of a rectangle is length times width. The width here is 1. The length or height, if you would, is also 1. So we would say that with just one big old rectangle, that we have 1 square unit. But now we can dive deeper into this and let's say, okay, maybe I have, whoops, 2 rectangles. Whoop. Here's my 1. Here's the point, 1, 1. Now, what if I split it in half? And here, I'm going to go with the overestimate using right-handed limits, because notice, here's my sub-rectangle. I go to the right, I hit where I am on the function, and whoop, go left. Here is my second rectangle. I go to the right wall, I go up to the Y, and then I come over and down. So again, the area of a rectangle is length times width or height, if you prefer, right? Because we're going up. So the width of both of these things is 0.5, right? We want equal distance. So it's 0.5. And then the lengths are going to be f of 0.5 plus our width, 0.5 times f of 1. So we know the width is a half. So 0.5 or 1/2 squared is 0.25 or 1/4. This is 0.5 times 1 because 1 squared is 1. So this is 0.125, yeah, or 1/8 plus 0.5. So overall, the width is 0.625. So we're now getting closer to what the actual area under this curve is, right? Here we see that we have only this area is what we want, but we have all of this extra. Here's what we want, but all of this extra. So what if, let me make sure they're both on the screen still. Move up so that this little box right here isn't there. Or maybe you can't see the box. Ooh, wow, I don't know. Anyway, I'll move it here. So maybe if I do, let's say 4 rectangles. 1, here's the 0.11. So now the width of all my subintervals is 0.25, right? Because 1 divided by 4. So my widths for everything is 0.25, whoops. So I can have that the area is just 0.25 times the sum of all of these subintervals. Let's just keep with the right hand so that we can compare apples to apples. Whoops, pretend like that's, picturesque. Notice here we have less overage, even less overage of what we want. So the more rectangles, as you can imagine, the better the estimation is. So this would be f of 0.25 plus f of 0.5 plus f of 0.75 plus, oops, forgive me, f of, 1. So the area is equal to 0.25 because that's all the widths, right? So same thing as up here is if I factored these out. Oh, I should have changed colors. Y'all forgive me. So 1/4 squared is 1/8 plus a half squared is 1/4. 0.75 squared is, that's harder for my brain. That would be what? 3/4. So, oh boy, 9/16. 9 squared, sorry. Yeah, 9/16. You aren't here to correct me, so I have to check myself. What a bummer. Okay, so now if we're adding all these up, I have 1/8 plus 1/4 plus 9/16 plus 1. So that's 1.9357. This is 0.25 times 1.9357. Oops, 7. 5. There we go. Now times the 0.25 because that's the width. So my area under my approximate area, I should say, is 0.4843, or let's say approximately 0.48. Again, if y'all see a mistake, forgive me. You're not here to catch my crazy human errors. All right, so again, we're getting closer and closer. We had 1, we added more rectangles. We're at 0.625. More rectangles, now we're at 0.48. And just so that we can, or I can show you one left-hand limit. So these are all right-hand limits. This is a left-hand limit. These are all right-hand, not limit, sorry, right-hand estimations, subintervals. That would look like this. Here we go. There's our point right there. Here's 1. So if I want to do 4 subintervals again, well, now I start on the left of all of these rectangles and go over. Okay. So this, in this case, this is an underestimate because notice there's some white gappage there. This is an underestimate. The widths are all still 1/4 or 0.25, but now our lengths, respectively, this helps if I can write, oh boy. There we go. Lengths are f of 0, f of 0.25, f of, where am I? 0, 2.5, 0.5, 0.5, and f of 7.5, 0.75, which we know is 0. Sorry, I should have done this a different way. 1/8, 1/4, and this is the 9/16. Cool, so now we add these up. That's 0 plus 0.125, that's an 8, plus 25 plus, let's see, that's 9/16. Oops, see, I caught it. Bet y'all were wondering if I was going to get it. I did. Plus 9 divided by 16 is 0.9375 divided by the 0.25, or excuse me, times. There we go. So here the area is approximated, let's say, to 0.23. So we're getting closer, but notice overestimate, way underestimate. Because this is just the x-axis here, right? That's just the line. There's not even any width to it, or excuse me, there's no height to it, if you would. Okay, so the takeaway from here is that we are just adding up rectangles. You will be told how many rectangles to do, whether you're doing the left side or right side, and then you're just gonna add them all up to get this approximate, right? Like I said, approximate, the estimate area under the curve. On Wednesday in class, we'll talk about how we get the exact area under the curve. But as you can imagine, it's by taking a limit. So it may be more accurate to choose a partition specific to the function, but sometimes it's easiest just to choose subintervals of the same length. which is what we just did on this page, right? I did 1 and then 2 and then 4. So subintervals of same length just kind of makes things nicer because all of the widths are the same. You're just multiplying by the same number, all that stuff. For this interval, for the interval A to B on the closed interval, on which we want the approximation, choose a number of subintervals in and compute the width of each subinterval. So basically, what we did here, well, the change in x, so the width in x, is b minus a over n, how many intervals we wanted. So if I wanted 4 intervals, that would be 0 plus 1 divided by 4, which gives us the 0.25. If I want 2 subintervals, that's 0 plus 1 is 1 divided by n. Our number of subintervals gives us a half. Cool. So this tells us our width. Then we determine how to choose the rectangles. For this class, we will use left, right, and midpoint choices to figure out which points to use for the approximation. Oh, to figure out which points to use for the approximation, find the width, your delta x or change in x, and use that to determine your endpoints. For left endpoints, you start with A and keep adding your delta x or your width. For right endpoints, start with A plus the width and end with B. For midpoints, you will have to calculate them by hand. We will see how to do this in an example below. We still use a Riemann sums, which adds up the areas of rectangles that approximate the correct area. So that's what we're actually doing. So what we're doing when we add up the rectangle is called a Riemann sum. Okay, this was a person way back in the day, their last name, and then sum because we're adding them up. So here, say we are still using, or, well, no, okay, new function, I lied. I thought it was from the first page, but it's not. So if I have this function here, okay, this is a partition of A to B into subintervals. They're saying our subintervals are x1, x2, here's a random one, and then B, however many random ones we want. Well, if I want to construct the rectangle above with the subinterval, well, here, if this is where we start, and then I choose this to be my next subinterval, okay, here they're using the midpoint. Oh, here it is, sorry. Here's my x sub 1. So here's my subinterval, random, subintervals. So the dotted lines are what they are using to approximate the heights for. And this, like, they're emphasizing, they meaning the book, emphasizing that it's totally random, that we don't have to do midpoint left or right. We can choose whatever works for us, okay? Because perhaps maybe this is an even number on the y, right? It might be like 2, 3, 1, I don't know. So it could just be numbers that work, that makes sense. But if I want a midpoint, so let's say I can draw. So first, that's a big assumption. Ooh, okay, fair enough. Let's say here's my A, and here's my B. And suppose I just want 4 subintervals. 1, 2, 3, 4. For sake of argument, let's just say that this is, well, it doesn't really matter. X sub 1, X sub 2, X sub 3. And then this would be X sub 4. If, oh, we want midpoint. So here's a midpoint. Yeah, let's say this is just 1, 2, 3, 4, and 5 for easy math for my brain. Then the midpoint is literally the middle point of these numbers. So for all of these rectangles, so I'm gonna change colors. Here's the midpoint. Do, 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 do. Boop, 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 boop. Y'all enjoying my noises? Probably not. Gotta entertain myself somehow. Okay, so here are my rectangles. Here are my midpoints. Okay, so that means that the height or length, if you would, length, height. If this is 1, 2, 3, 4, 5, we would want f of 1.5, f of 2.5, f of 3.5, and f of 4.5. Oh, make sure I'm on the screen. I am not. You're literally just in the middle of your rectangle. So the middle of 1 to 2 is 1.5, 2 to 3, 2.5, 3 to 4, 3.5, 4 to 5, 4.5. Okay. These are your middle, your midpoint choices. Midpoint choices. Okay. The width of all of them is, of course, 1. So you would add all of these up, and then that would be your approximation. Next. Okay, so I'm going to stop this video to make a new one so it's not crazy long. Oh, hang on. Here's the button. Here's the button.